Okay, hi guys. Yeah, let's do some maths. Let's get straight on with it. No messing about today. We're going to do AQA FP2 Jan13, same paper as the last episode, and we're going to be having a look at question 7, which is a question on proof and proof by induction. But the induction works slightly differently to the way you'd normally do the induction. So it might have thrown a couple of you, but we're going to have a look at it now, so it should be okay. Okay, get the question paper open in front of you. Turn to question 7 on page 16, and let's get on with it. So we're given a polynomial, p of n. Oh, right, that should do. P of n. And p of n is n minus 1 cubed plus n cubed plus n plus 1 cubed. And in the first question, in A, we want to show that, and I'm going to write this out as you would do if you were answering this question. So WTS stands for want to show. We want to show that p of k plus 1 minus p of k is a multiple of 9. And the way you can write a multiple of 9 is 9 multiplied by any number, any integer. So if we want to show that this is a multiple of 9, let's write down, we want this to be equal to 9m, where m is an integer, where m is a member of the integers. I explained what that meant in our last video. Cool, I just picked the letter M out of thin air, probably because it said multiple, so the letter M was in my head. So we want to get the left-hand side equal to the right-hand side. Only one place to start here, the left-hand side. You can't do anything with 9M. So let's dive straight into it, and let's have a look at the left-hand side. So, left-hand side, LHS, is equal to P of K plus 1. So K plus 1 minus 1 gives me just k cubed, and then k plus 1 cubed, and then plus k plus 2 cubed. And now we're going to take away, and I'm going to stick this inside a square bracket, because I know there's going to be circular brackets. Well, they're all over the place, aren't they, in this question? K minus 1 cubed plus k cubed plus k plus 1 cubed. Cool. And already, straight away, we can see that some of these cancel out. I'm looking for a red pen. Here it is. Red for cancelling out. So this plus k squared here cancels out with the minus k squared. You can see the minus outside the brackets. And k plus 1 cubed, not squared, sorry, k plus 1 cubed cancels out with this minus k plus 1 cubed. Cool. So we're only left with 2 terms then that we've got to prove make a multiple of 9. So we've got k plus 2 cubed minus k minus 1 cubed. Now what's going to help me expand cubed brackets quickly is remembering the pattern of the binomial expansion, and all the coefficients come from Pascal's triangle. So if I just write that down now, 1, 1, 1, 1, 2, 1, and then the third line, it really is the fourth line, but the third line, 1, 3, 3, 1. So that's what our coefficients are going to be when we expand this binomially. And the pattern is you get the highest power of this multiplied by the lowest power of this, and then as you decrease this power by 1, you increase this power by 1. So the first term is 1 multiplied by k cubed, and then the next term is 3 multiplied by the power of k comes down by 1 to make 2, and then we've got a power of 2 to the power of 1. And so the next term then is plus 3 times k times 2 squared, and then just 2 cubed. So you decrease the power of 1 and increase the power of the other one at the same time. And we take away from that exactly the same pattern. K cubed plus 3 times k squared times minus 1 plus 3 times k times minus 1 squared. Now this is somewhere where normally people who study just maths, like C2 and C3, classic mistake is forgetting the brackets in your binomial expansion if you've got a negative. That's a real classic, that one. Used to catch people out all the time, and then plus minus 1 to the power of 3. So you need brackets there as well. And again, we can see that we've got a few things cancelling straight away. So this k cubed cancels out with that minus k cubed. I think those are the only ones that do. Yep. Okay, now let's work out what our terms are. So we've got 3 multiplied by 2, that'll give us 6k squared. 2 squared is 4 times 3 is 12, so plus 12k. And then 2 cubed is 8. And from that we're going to take away 3 times minus 1 is minus 3k squared. Minus 1 squared is plus 1, remember that, plus 1. And then that's plus 3k. And minus 1 cubed is minus 1. Again, very important to get your brackets there. So 6k squared, take away negative 3k squared is 9k squared. 12k, take away 3k is 9k. And 8, I'm sure that wasn't the number that I got when I did this a second ago. Yeah, I did this wrong. I did it wrong a second ago. Plus 2 cubed is 8. Minus 1 cubed is minus 1, so that gives us 9. Or we're here, aren't we? 8 take away negative 1, so 9. And they've all got 9s in, so that's good. So factorise out the 9, you've got 9k squared plus k plus 1, which equals the right-hand side, because k squared plus k plus 1 must be an integer, so that does equal 9m, which was our right-hand side. Lovely. 3 marks there. And the next question, which is quite weird, it's 4 marks, but I'd say it really relies on you spotting something that's kind of like a 1 mark spot. So it's a lot easier than this question for 3 marks. It's a little bit weird. Worth mentioning there how I laid out the proof. So I said right at the beginning what I wanted to show, and then I started at one side, the left-hand side, and worked my way to the right-hand side. So what we know now, I'm just going to write this at the top. So in part A, the question we've just done, we proved, so we know this now. I'll write out the function again. P of n is n minus 1 cubed plus n cubed plus n plus 1 cubed. And we now know that P of k plus 1 minus P of k is equal to 9, and I'm going to still call it m, but that's really 9 times any integer there. Okay. Prove by induction that P of n here is a multiple of 9 for all integers n greater or equal to 1. So we're going to start off setting it out exactly as we would a proof by induction, but like I said, it's going to require you to spot something halfway through this proof. So it says prove it for all integers n greater or equal to 1, which means the smallest integer that it could work for is 1, which means our base case, so let's lay this out properly, base case is n equals 1. So in that base case, P of 1 is, well, 1 minus 1 is 0, 0 cubed is 1. No, it's not. What am I on about? What an idiot. 0 cubed is 0, obviously. 1 cubed is 1. Plus 1 plus 1 is 2. 2 cubed is 8. 1 plus 8 equals 9. So our base case works out great. Okay, how does induction work? You assume the thing is true for one number, and then you prove it's true for the next number. So let's start with that. So assume for n equals k. So assume for n equals k that p of k is a multiple of 9. So we're going to assume, that means for now it's true that p of k is equal to 9 multiplied by a. That p of k is a multiple of 9 is what that means. Now I want to show for my induction then that this is true for the next number up. So I want to show for n is equal to k plus 1 that p of k plus 1 is also a multiple of 9. Let's call it 9b. So this is my assumption, and this is what I want to show. Now, if you were doing a normal proof by induction at this point, the normal thing to do would be to say, okay, let's start at the left-hand side. What's p of k plus 1? Let's stick k plus 1 into here, and let's see how I can use this fact, what I've assumed, somehow to get to the answer. That would be what you normally do. However, something in the question can help us already. And there's a hint here that the question doesn't go A, B, C. This is A part 2. So that means you're going to have to use A part 1. If it's A part 2, you're going to have to use A part 1. What have we found out in A part 1? Well, we found out that the difference between pk plus 1 and pk is a multiple of 9. Now this is what you have to spot. If the difference between pk plus 1 and p of k is a multiple of 9, and pk, by our assumption, is also a multiple of 9, so we've got the difference between two numbers is a multiple of 9, and one of those numbers itself is a multiple of 9, must mean that the other number, pk plus 1, what we want, is also a multiple of 9. So let's write that out. That's what you had to spot, now you need to get the marks. So, still though, in our proof by induction, this is set out exactly how we would as a proof by induction. We're just doing this inductive step now a little bit differently to how it's normally done. So from part A, so from AI, so from A part I, P of k plus 1 minus P of k is equal to 9m. That's the first factor we're going to use. Now from our inductive hypothesis, so from IH, you should write out inductive hypothesis. From IH, from our inductive hypothesis, PK is equal to 9a. So if we put those facts together, you could even call this equation 1 and equation 2, and you could say substituting 2 into 1, although you probably don't need to do that, that's overkill really. Just on a new line, if you wanted to, you could write the imply symbol. So putting those two facts together tells us that 9, that's not a 9, it's a P, isn't it? P of k plus 1 minus P of k, which is 9a, equals 9m. So that means P of k plus 1 is equal to 9a plus 9m, and that must be a multiple of 9m. 9 lots of a plus m. As required. And then, after this, a sentence then, by induction, P of k, or P of n, is equal to a multiple of n for all integers n greater or equal to 1. You should finish with that sentence there. By induction, for all integers n greater or equal to 1, P of n is a multiple of 9. So, bit of a different one there. Like I said, your clue was that it was part AI and then part A, II. But yeah, it required you to spot something. So we lay it out exactly like how we would do induction. But when you get to this step, instead of thinking, oh, I'm going to start with the left-hand side and work my way to the right-hand side, you really needed to spot that we've got a number minus another number is a multiple of 9, but we've assumed that one of these numbers itself is also a multiple of 9, so the other one must be as well. Cool. My throat is getting a bit sore today because partying too hard at the weekend or something. Take a little drink. Oh, just a nice bit of vodka there just to wake me back up. Lovely. Okay. Last question for 2 marks. And it starts off by saying using A part 2. So really, they could have called this A part 3. But then if I guess if they did that, then the whole question would have just been A, which is a little bit odd, isn't it? Maybe that's why they did that. So it says using your result from A part 2. So I'm just going to write down that result again. So we found that P of n, which is 9n minus 1 cubed plus n cubed plus n plus 1 cubed is equal to a multiple of 9. So I still call it 9n. So using that result, we want to show WTS. We want to show that n times n squared plus 2 is a multiple of 3. Let's call it 3z because I've used A and B already. So that's what we want to show. So I'm thinking here, n times n squared is n cubed, so it is going to be something to do with this. What do I have to work with here? I know it's 2 marks, so it's not going to be anything too tricky, probably just manipulating algebra. Not much I can do with the left-hand side here. I can expand it, n cubed plus 2n. So yeah, so what, mate? You know, that's not going to get you anywhere, is it? So let's start with what we know then. Let's start with this result that we know at the top, and let's expand this and see where that gets us. Now we've still got Pascal's triangle, so this is going to go really quickly. There's your Pascal's triangle, and nice little trick is if you've got -1, an odd number, because not an odd number, what am I talking about? Yeah, no, that's right. If you've got -1 and an odd power, you know your terms are going to alternate positive, negative, positive, negative, positive, negative. Because that -1, whenever it goes to an odd power, will always be a negative number. So we can expand this really quickly. So n cubed minus 3n squared plus 3n minus 3, 1. That's a mistake I made earlier as well. So it alternates like that. And then plus n cubed plus n cubed plus 3n squared plus 3n plus 1. And that is equal to 9n. Okay, so what have we got there and how does it help us? How many n cubes have we got? 1, 2, 3 n cubes. How many n squares have we got? We've got minus 3n squared plus 3n squared. They cancel. And then we've got 3n plus 3n. That gives us 6n. And then -1 plus 1 cancels. So that is equal to 9n. And now you can see, hopefully you can see you're homing in on it. Not too much left to do now. Divide both sides by 3, give us n cubed plus 2n is equal to 3m. And then factorise out the n here. That gives us n times n squared plus 2 is equal to 3m, which equals the right-hand side. Tick as required. Doesn't matter, the letters are different because I just picked Z out of anywhere, don't I? Cool. Yeah. So, we spoke about how to lay out your work, which is really important, and it helps me sort of remember what I'm doing. If I think, base case equals 1, then I assume something, then I write what to show, then I normally start at the left-hand side. That gives me a nice little procedure to run through, so I'm not thinking, oh, what am I doing here? I don't know. Yeah. But this induction required a little bit of a spot, didn't it? It required you to realise you're in the same letter of the question. This is A part 2. And how do you spot that? I guess you just take your time through your work. You have in the back of your head what you know at every point. And yeah, you look at what you know, and you look at where you're going, and you see if you can bridge the gap some way. Cool. Hopefully I'm going to do another video tomorrow on question 8. As always, any thoughts, questions, comments, queries, words, put them in the box below, and I'll definitely answer them. Honestly, I haven't got anything else to do, so just please. Right. That's it for today. Good luck, guys.